Welcome back. Today should be a relatively quick lecture on video, but there are plenty of places to stop and think about what code on the slide does before watching the traces, so I entreat you to do that. Today we're going to expand our horizons yet again. All semester we've been dealing with programs that consist of a single process. But now we're going to see how to write programs that interact with additional processes of their own creation. This is going to be fundamental in how we go about the last assignment in the course, building your own shell, a program that, at the user's request, executes other programs. The appendix of the Exceptions and Processes lecture last week showed many Linux system-level functions. Recall these are functions that go into the OS kernel to do work on your behalf that require special permissions. So if we think of the Linux OS as a module, those system-level functions are the interface to that module. The appendix groups the system-level functions into categories. One of those categories was process management, and that's what we're talking about today. Specifically, we'll study exit to terminate a process, fork to create a subordinate process, wait to wait for a subordinate process to terminate, and the exec family to change the program a process is executing. Precepts will cover getPID to help in understanding what's happening, but we won't need it in lecture nor in assignment 7. A shell is certainly one example of a program that will have to create processes. When the user requests a program P to execute, the shell, which is a program in execution, thus a process, must create a new process for program P to execute in. Another example is a server that, when it receives a request, will delegate handling that request to a new process so that the server can continue listening for additional requests. Now, how to achieve this? To abstract away from a specific program like the shell or a web server, let's use the general hierarchical terms parent and child. One might think there's a way to create an empty child process not affiliated with a program and then tell that process what program to run. Or one might think that there's a way to say, create this child process using that program. But it's a bit odder than that. The mechanism here is perhaps not immediately intuitive. The parent creates a new process, and that new process is in fact an exact copy of the parent. Then the child will issue a command that says, I no longer wish to be the same program as my parent. Please make me this other program instead. I suppose this is the teenage rebellion in the process concept. We'll cover each of these steps separately. First, the process creation. The system-level function that creates a new duplicate process is called fork. We'll often use that as a verb, to fork off a child process. Fork creates an exact duplicate of the parent process, including processor state, memory state, etc., at the time of the call to fork. Having an entirely identical but distinct process state sounds expensive, but it better not be because we want to be able to fork off many processes, and further because any work that goes into the duplication will very often go to waste as the child process almost immediately overwrites itself to become a new program. Fortunately, we can avoid most of the pain of copying the entire state of the process, because there's a mechanism called copy on write that hinges on the observation that if a duplicated resource, memory in this case, is not modified, the resource can be shared between the two copies without being physically duplicated. This sharing can continue as long as it is convenient, perhaps until data is evicted from physical memory, or potentially deferred all the way to the first write, when the two processes' corresponding data diverge. Some virtual pages may never need to be duplicated. In the previous slide, it said that there is a single solitary difference in the parent and child copies, and it's the return value from fork. Because fork is unique in that it is called once, but returns twice. Specifically, what I mean by that is that the parent calls fork, and then both the parent and the child begin execution immediately after that fork. The only difference between the parent and child processes, then, is the return value of fork. The child gets a returned value 0, and the parent gets a returned value with the child process's ID. Recall last week's lecture we talked about how every process has its own unique PID. This is a crucial difference because it allows us to program in a conditional that is able to differentiate the parent from the child. So each process can now know which of the two it is. But before we get into that, let's think a little bit about what it means to have multiple processes running at all. As a reminder from previous lectures, when there are multiple processes running, the processor will context switch between them, typically frequently, in order to give the illusion of their own private control flow in perfect parallel. And on most modern machines, there are multiple processors, so processes can run in actual parallel. But we're still often going to talk about the system as though it has only one processor. So now that we have multiple processes in our program running concurrently, they're competing against each other for resources. In this case, most notably being the running state on the one processor, instead of the ready-to-run state waiting for that processor. Let's see an initial example. Take a moment to treat this like an iClicker question. What does this program print to standard out? Let's trace it out to see. We're going to start out with only a single process, and that process will, of course, start executing at the top of main. Before the fork call happens, the parent is going to print 1 followed by a new line. Then the fork happens. Now there are 2 processes, each the same, each running the same spot in the program. But if we're considering only a single processor, they can't both really be running. And, like all discussion we've had thus far about context switches, it's indeterminate which of them will be in the running state. So we have no way to predict who gets to execute the return from the fork first and continue on with the program. Let's imagine in this case it's the child. So now the child will print 2 and a new line. After doing that, if it wasn't context switched away back to the parent, the child exits. With no further contention from the child, the parent can print 2 and a new line. And then the parent can return and exit. So the answer to our iClicker question was 1, 2, 2, as seen here. But what about if the parent got to run first instead of the child? Let's quickly run through that instead. Again, the parent starts off and prints before the fork. Again, the fork happens, and now there are 2 processes executing. In this case, now let's say that the parent gets the processor and is able to print its 2. The parent keeps the processor and returns and exits. Now the child is alone and can print the second printf of 2. Then the child returns and exits. So in this case, we have the exact same output, except the ordering of the 2 outputs is different. We can't distinguish it in this case, so in this program it didn't really matter. But as we saw briefly, after the fork, we can have code that is conditional on the return from fork, so the parent and child could be doing different things. When that's the case, we'll have to repeat our steps here and consider 2 different branches of execution when predicting the program's behavior. Frankly, it's even worse than that. Because of context switches that can come almost any time, our space of possible execution orders is every possible interleaving of the 2 processes' instructions. Let's explore that a little bit further with another iClicker Home Edition question. Pause the video and look at this code. What does it print? It includes that conditional differentiation between the parent and the child with different operations for each. So now we can't just look at one and then say, oh, it must be that. The answer here is E. It's either A or B, but the order is uncertain. Whichever one runs first will change the value of X, and so assuming that this value is in memory and not just sitting in a register somewhere, copy on write will ensure that the two processes actually have different distinct copies of the memory and aren't impacting each other. If it's in a register, then that's fine. Context switches, we already know how to handle switching out register values. So the child will decrement and thus get 0, and the parent will increment and thus get 2. Let's take a closer look. Before the fork, we have x gets 1 and PID with some garbage value because it wasn't explicitly initialized. The parent forks, and now there are two processes with distinct state, so each has their own copy of x. Imagine that the child gets the CPU first. It will have a return from fork of 0, so that will be the value of PID. Note that this means PID is sort of a misleading variable name, since the child process is not process 0. In fact, there's never a process 0. That's why fork is able to return 0 in the child. But it is certainly customary to return fork into a variable that says something like PID as opposed to return from fork. PID is actually more meaningful, even if it's sort of misleading. The value of the variable PID is 0, so we enter the consequent. X in the child decrements, and we print. Changing X in the child does not affect X in the parent. We've printed 0 here, but the 1 value in the parent is still hanging out. The child then calls the exit system level function, which exits the process. Now the parent gets to run. It's still way back at the fork. Its PID variable gets the value of the child's process ID. Note that in this sequencing of this example, the child has already run and terminated, but the parent will still get the PID that the child had when it's running. We'll see why this is important for maintenance purposes later. The parent's PID is non-zero, so we execute the code in the alternative. And then the parent exits, again with the exit system level function. Now we see that the output for this program was the child's print first with 0, and the parent's second with 2. But of course we made the choice in that execution that the child would get to go first. What about if the processor gave execution to the parent first, and then like in our previous example, the parent got to keep the processor all the way until it was done? The parent would call fork, the OS goes off and creates a duplicate process, and now the parent runs first. Returning from fork, PID gets the child's PID. We execute the alternative, and so X becomes 2 and we print that. Changing X in the parent doesn't change X in the child, so it's still sitting there with a value of 1. When the parent exits, that frees up the CPU to let the child run. And so in the child, fork will return 0. This will trigger the consequent where the child will decrement X to 0 and print it. And then the child can exit. So in this case, the output was parent 2, child 0. So back to the iClicker question, the answer was E, that it could be either child 0, parent 2, or parent 2, child 0. We can't know which order the CPU will choose. As proof, on the bottom of the slide, here's the execution of many runs of this program on ARMLab. While it's overwhelmingly the case that at least for this program, ARMLab chooses to have the parent run first, it's not absolute. There's one last question arising from this code. Instead of returning 0, we exit 0. Should we have done that? Is it even right? Pause the video and think about it just for a little bit. The answer here is B or C. The code is correct, but it would have also been correct had we done return 0 here instead. But think about what would happen if, instead of being in main as we are here, we were several functions deep in the call stack. In that case, returning wouldn't kill off a process. It would just continue running, and the program in the function that called the function that forked. That could end up either being really tricky to differentiate which process I am, parent or child, or if the child was never intended to return to the continuing code anyway, it could cause serious bugs. So it's a common idiom that one of the child or parent, or perhaps both, will have an exit instead of a return. Keep a lookout for this in your shell, particularly as you handle failures, where it's practically muscle memory at this point to return some failure value. In the previous example, the ordering of which process ran first mattered for the output, and that will often be the case. But if we're beholden to the whims of the OS and the CPU, how can we write code that handles a program's requirements about ordering? The wait system-level function suspends a process from running until one of its children terminates. Then once one of its children terminates, the parent will wake up and continue execution. This allows us to enforce an ordering. The CPU could let the parent run first, but the parent can say, "No, I'm not going to do anything right now. Let my kid run." Note that the return value is the PID of the child process that terminated, and it takes an argument that is used as an out parameter to fill out a sorted status. In this class, we typically are content to ignore that additional information and just supply null as the argument. And for our shell, we don't really care about the return value either. There's only one program in that the user is running from the shell prompt at a time, so only one process terminates to wake up the parent process. Intricate wait examples with many processes and using the PID return value do make for enticing exam questions, however. Let's start, though, with something not quite so intricate. Here's a program that forks as we've been doing, but now has a wait call as well. What will it print? Pause the video here and see if you can trace it. The answer is A. Let's trace. The parent forks, and we have two processes running. Let's first consider that the parent is chosen to run first. We skip over the consequent and go to the implicit alternative, since it's consequent exits. The parent doesn't take advantage of being called first, and instead asks the OS to put it on ice until the child terminates. So the child starts running back at the return from fork. It establishes itself as child, prints, and exits. After the child exits, the parent wakes up and does its own print, and then it can return. So with the parent first, child, then parent print. Now how about if the child runs first? Back to main, the parent forks. Now there are two processes. The child gets the CPU here in this case. It enters the consequent, prints, and exits. Then the parent gets to run. It calls wait, and wait returns immediately because the parent already has a child that has died and has not yet been waited on. So the parent can continue to print and finish. Just like before, we have child, then parent printed. We have successfully controlled our process execution order via wait. This isn't changing who the OS lets run first, but rather manipulating the code so that no matter the OS's choice, we can choose which code will execute first. Now we've seen how parents can wait for their child process to terminate. Sometimes we need them to in order to get correct ordering of operations. But even when we don't, it's still considered good practice that a parent should wait for each of its children. If the parent doesn't, the child will end up in one of two statuses, each with a very evocative name, orphan and zombie. And in fact, potentially the combination of the two, orphan zombie, though the latter is fleeting. Orphan just means that a process that is running has its parent already having terminated. This means the parent clearly didn't wait. Zombie is a process that has terminated but has not been waited on. Maybe the parent eventually will, maybe it won't. These statuses are potentially problematic because zombie processes hang around until somebody reaps them. So if, for example, a system daemon process that is intended to run forever sometimes forks off children, if it doesn't wait for its children, they'll just start to accumulate as more and more and more zombies running on the system. Let's look carefully at two cases. If the parent process terminates first, the child becomes an orphan. This means that the parent can never wait for the child since it's already terminated. To avoid the orphan turning into a permanent zombie, we need some other process to agree to wait on the orphan eventually. Traditionally, that process was always the OS's system initialization process, called init, which has PID 1 and is an ancestor of every process. It was said to adopt the orphan process, because we had to continue the familial theme. In more modern versions of Linux, any process can state that it is willing to be a so-called sub-reaper ancestor that fulfills the role of init just a bit farther down the family tree. The way this happens is that when an orphan terminates, briefly becoming a zombie, its nearest living sub-reaper ancestor, init in the worst case, will receive a signal sigchild, indicating that it should wait on the newly terminated orphan. The other case is if the child terminates first. It now becomes a zombie, but its parent is still alive, so there's some hope that the parent might do the right thing and call wait. If it does, everything's good. The zombie is reaped. If it doesn't, then when the parent exits, we return to the previous case. The now orphan zombie remains so for only an instant before being automatically adopted and reaped by a sub-reaper ancestor process or init in the worst case. Of course, if the child never exits, then hopefully it's a daemon process that's intended to, because otherwise that's an error state with a runaway process consuming resources. Thus far, we've mentioned a few times that after forking, the child process can overwrite itself to be a different program. The way it does this is with one of the exec family of system calls. Exec replaces the process's current program with a different program, sort of like a theater quick change of costume. There are a bunch of varieties of execs, basically permuting the options of does it search the path for the command name, does it take an array of arguments, and does it take an array of environment variable mappings. In the example on the slide, execvp, the v means it takes an argument vector, and the p means that it searches the path environment variable. The lack of e means that it does not take an environment variable mapping array to be used in place of the existing environment. So the way it is called is with a string for the command name and the array of argument strings, which by convention should start with the command name, just like we've seen the argv0 has the string for the command. And then the requirement is that it must have the last entry be null, just like all the argvs we've seen. Here's an example. If we wanted to programmatically set up a call to exec, we could have the command be just a pointer to a string in RO data. The args array we'd need to arrange ourselves though. For example here, as a block scope variable with each element pointing to an RO data string, except for the last one, which is null. Then with the command name and its argv set up, we can call execvp to transform the running process into cat. Recall that fork was unique because if it is successful, it returns twice. Well, exec is similarly exotic because if it is successful, it doesn't return at all. It just moves on with its life to be the new program. And since that new program has a different text section, whatever your next instruction after the exec is in your program will never get executed. Ideally, exec should always work, but as we've seen in this class, we should always anticipate things going wrong. And indeed, execvp could fail for various reasons, the most common of which is that the command given doesn't exist or isn't in your path. So because it could fail, and thus could end up continuing in your code after the exec, you should catch that case, which must be a failure. Let's do one more trace to see the details of how we use exec. Again, pause the video and answer, what would this program print to standard out? What processes exist over the run of this program? The first thing that main does here is to build a command name and then an argv that will be passed into exec to specify the program we want to transform ourselves into. Note that there are no forks in this program, so there's only ever going to be one process. Then we call exec. Cat is a real program. On our system, it's found in /user/bin/cat, and /user/bin is in our path, so this exec should succeed. Cat will have argv0 to be cat, and argv1 to be readme, and no additional arguments, indicated by reaching the terminating pointer to null. Thus, it writes the contents of the file readme. This is my new line readme file. And with that, it terminates. The fork plus child exec parent waits combination is a tremendously common idiom. So much so that there's a shortcut for it, the system function, which combines all three in their usual pattern. In the remaining time in this lecture, I'm going to talk about the structure of what a shell is and take a look at an absolutely minimal version of it to start to think about assignment 7. A shell is really just a big loop. In step 1, we read and parse the user specification of what a program that they want to run is. Step 2, fork a child process. Step 3a, in the parent, wait for the child to finish. In step 3b, in the child, call execvp to execute the command for the specified program. Step 4, back in the parent, after the wake up from wait, after the child exits, clean up anything required. And then step 5, go back to step 1. So here's some pseudocode mixed with real C for this structure. In pseudocode, we parse our command from the user, and we set up the command and arguments to be passed into exec. We fork. Here, imagine that the fork succeeds, so there's a child process, but just like always, we should have code that says what happens if fork doesn't work. If the parent ran first, it waits immediately, so the child can run. If the child ran first, well, it's running. So in either case, we're in the child, where PID is 0, and we call exec. If it works, we're no longer here. And if it fails, we clean up. The child will then continue running some other program in its process, and eventually finish. In the parent, where we've been waiting for the child, we wake up, and we set back up to go again. In your shell, your commands are going to be blocking. The shell doesn't regain control at the prompt until the command finishes. But in Bash and other shells, that's not the case. We can choose to put a process in the background and get our shell prompt back immediately. How does that work? The way this happens is we don't wait in the parent after the fork. That means the parent will keep running even as the child is running concurrently. But that also means we won't be waiting for the child to terminate. Indeed, then we'll get to run more and more different commands, and instead of having one child, we'll have many children. So we have to periodically try to see if it's time to wait on them. We can use a variant of wait that waits on a specific process. Giving it w-no-hang as an option means not to block, return immediately if if that child hasn't exited. Or if we've received a sigchild signal, which we've said was sent to the parent when a child exits, we know that one of our children has terminated, and we can just do a wait in the handler. This is not part of the Assignment 7 specification, but hopefully it gives you some insight into how the shell you use every day works. Recall that we said that fork was surprisingly not expensive, thanks to laziness and virtual memory. The answer is largely the same here for exec. The expense of loading pages from disk into memory is spread out over time thanks to how virtual memory works. So exec is similarly efficient. So instead of a summary slide today, I'll just leave you with this one overarching pattern for the shell. Even if it's not due until Dean's date, which seems impossibly far away right now, I promise you it's not. Of course, you should all finish Assignment 6 first. That's due next Thursday. But if you finish early, it would give you more time on the shell or, your other classes. Have a good rest of the week, a great weekend, and I'll have another 2 lectures for you next week, which will be our last week of classes.